Suppose I were to draw this function here, or I gave you a function, and I said, all right, let's choose two arbitrary points on this function. I'm just going to just randomly choose two different points here, which kind of fits my purpose. All right, so let's go ahead and label this first point P and this second point Q. And I'm going to go ahead and I'm going to draw a secant line. That is to say, a point between that runs through these 2 points. I'm going to make that a little bit thicker so we can see it a little bit more easily. Now, suppose I had these points here and I wanted to label these points. So let's actually call this point P, and let's also indicate its corresponding x value. Let's call this x, and this right here would represent its y coordinate or its y value. So there's its x and there's its y. Now, I'm going to do the same thing for the q here, and I'm going to label this one, actually I label this one x2, and just so we don't get too mixed up, I'll call that x1. And in the same way, I'll call this point here x2, or y2, excuse me, and this one y1. Now, all I've done so far is just label the points. And now, if I wanted to find the slope of this secant line, well, what do we know about the slope? Well, you just know it represents the vertical change over the horizontal change. So in this case here, I would take y2 minus y1, all of this over x2 minus x1. And that's the basic formula for slope. So that represents how much it's changing vertically with respect to how much it's changing horizontally. And we know that. We've been working with that for a while now. If you're in this course, you've definitely seen that before. Now, let's think about these points somewhat differently. Instead of thinking about them in terms of just their x and the y, let's think about them as inputs and outputs of a function. That is to say, and I'll change the color here. Let's go to purple just so we can see this. Instead of calling this point here x, let's label it x still, just x. That means, though, this y value, we're going to represent it as f of x. That is, it's the function evaluated at x. Now, similarly, this point over here, I'm going to call this point here x plus h, where that is, it is an h distance away from where this x here was. So we're defining this value or labeling this value with respect to this x here. We're saying it's h units away from x. So what that means is now this y value, we're going to relabel as f of x plus h. So just to make sure we understand, we've got the input, we've got the output, x and f of x. F of x plus h is the output of the x value, x plus h. Now let's take the same slope here, and now let's rewrite it in terms of in the way we've rewritten these coordinates. So we're going to say f of x plus h, excuse me, minus f of x, all of this over x plus h minus x. And one quick look at that, we can see that x and negative x are going to negate one another, so we're just left with this. Now, if you're looking at this, you should probably realize that this should look pretty familiar to you. This is what's known as a difference quotient. We call this a difference quotient. So we've got the difference quotient here, and you may have seen that before previously in pre-calculus. And if you remember then, that difference quotient is just simply a way of describing the slope. It's another way of describing the slope. So we're going to say fancy slope. That's really all it is. So now that we can think about the slope as a difference quotient, I wanted to kind of pose a question here. What would happen as h starts to approach 0? Ask yourself, what would happen here as h starts to approach 0? Well, pause the video and think about what that would mean. Well, as h approaches 0, this point Q has no choice but to start moving to the left. As h decreases, this point Q, I can kind of show you what's happening now, this point Q would then start moving closer and closer to the left, right? So it's not too confusing, I'll remove those. But as h then gets very, very close to 0, this point Q is effectively going to be on the same point as P. In which case now this secant line will now be a tangent line. And actually, let's just draw it this way and see if I can just do this. Well, let's see. There we go. And I could probably move it a little bit closer, but you get the idea, right? I can extend that out. So this secant line now becomes a tangent line. Let me see if I can kind of demonstrate what's happening here a little bit better graphically. So let me just pull up my Desmos here, if it wants to cooperate. Okay, and in fact, let's actually just pull it up screen so we can see that a little bit more easily. Okay, so let me zoom out here a little bit. So pretty similar function here. So suppose we had, again, this is our fixed point. Now, you can see here, as h starts to decrease, let me pull this here. As h starts to decrease, let me move this here. As the distance between the 2 points decrease, notice what's happening to the secant line. Again, as h decreases, the distance here decreases, and that secant line becomes effectively the tangent line. And again, if I can pull this here, let me actually bring this out so you can see just kind of highlighting what's happening here with the h. You can ignore all the other stuff, but as h starts to decrease here, we start to get closer and closer to that secant line being the tangent line. And in calculus, we have a way of describing that process. It's what we have talked about thus far in this chapter. We can say that the limit of our difference quotient, the limit of our difference quotient, f of x plus h minus f of x, all of that over h, as h approaches 0. Okay, in fact, let me actually move this a little bit here. The limit of that difference quotient is explained as h approaches 0 is exactly what's happening here. This secant line slope, the slope of the secant line, effectively becomes the slope of the tangent line. So the limit of the difference quotient gives us the slope of the tangent line. And in calculus, we actually have a much more succinct name for all this. It is what's called the derivative. So there you have it. The derivative is actually just the limit of the difference quotient, which gives us the slope of the tangent line at any given point. So now that we have defined what the derivative actually is, now we can realize, we've talked a lot about how limits are so important to calculus. They're effectively what calculus is. Derivatives are simply limits. Integrals are just limits. So now that we know what a derivative is, let's quickly review some different notations for derivatives. I want to just highlight these here. We would read these as f prime of x, or you might see dy dx, or the derivative of f with respect to x. Dy dx, by the way, we can restate as the derivative of y with respect to x. You might also see something like y prime. You might also see something like this where we'd see dy dx, and all that means is the derivative of y with respect to x evaluated at x is equal to 3. Another succinct way of saying that simply is just f prime of 3. Now, before we try some problems, just to make sure we understand the limit process for finding the derivative, it's important for us to note here that we can say the following. We could say that not all functions have derivatives at every point. And the verb differentiate simply means to take the derivative. But let's go ahead and let's try a problem right here. Let's say the following. Okay, all right, let's try this. So we are going to use the limit process to find the derivative of this problem here. Okay, so let's do this. We're going to say f prime of x is equal to the limit as h approaches 0 of, and I'll write it once just to make sure that we remember what the difference quotient is. But this is the limit as h approaches 0 of x squared minus 2 plus h. And I'm going to pause right now because hopefully you're looking at this and you're thinking, that's not correct. Remember, common mistake, f of x plus h is not the same thing as f of x plus h. That's a common mistake that hopefully you got fixed in pre-calculus, all right? But so now that that is out of the way, let's do that correctly. We have x plus h, so we're evaluating x squared at x plus h, all of that minus 2. Let me highlight this part right over here, and I'll write the next part in its similar color. So minus f of x minus x squared minus 2. And again, hopefully you're looking at that and you're thinking, wait, that's not correct. Right, forgetting the parentheses here. Or you could just distribute that negative and write this as minus x squared plus 2. All right, now we can write all this over h. So now that we have that, if you're looking at this, and if I try to do direct substitution right now, I'm going to get indeterminate form, especially because I have this h in the denominator. So our next step is to try to use some algebraic practices or strategies, I should say, to rewrite this function. So I'm going to expand this out. I'm going to write x squared plus 2xh plus h squared minus 2 minus x squared plus 2. And I know that looks a little gnarly right now, but like in life, sometimes you need to make things a little messy in order to clean them up. Right, so now what I'm about to do right now is literally my favorite thing to do in all of math. I'm not even joking. I love simplifying here. All right, I love cleaning up polynomials. So I notice there's a negative 2 and a positive 2. Those are going to negate one another. I've got an x squared and a negative x squared. Those are going to negate one another. And I also notice that I have a common factor of h. Sorry about that. Common factor of h in each of these terms. So all of that can be rewritten simply as the limit as h approaches 0 of 2x plus h. It's beautiful. So now let's go ahead and just find the limit. The limit of all this as h approaches 0 is simply 2x. So we can say f prime of x is 2x. There is our derivative. We found the derivative using the limit process. And the second part is to simply evaluate that derivative at 3. So we can say f prime of 3 is simply 2 times 3, which is equal to 6. So make sure we understand what's happening here. We are saying that the derivative of this function is 2x. That is to say, the derivative of f of x is a function that tells us the derivative or the slope of the tangent line at any given point. And I can use that derivative to find the specific slope of the tangent line at the point x is equal to 3, which we found was equal to 6. Now, an alternative way of doing this is to use the alternate definition of the derivative, which I'm going to pause here real quick. If you want to take a quick screenshot of these problems, try these on your own and check them with the solutions I have in my School Loop Locker. But an alternate way of finding the derivative at a specific point is to use what's called the alternate definition of the derivative. So the alternate definition of the derivative is what I have marked down here. Now, at first glance, this looks very similar to what we just did. We have 2 points. We can find the slope of the secant line at these 2 points. And we can also find the limit of this difference quotient. But you'll notice that I've actually labeled these points somewhat differently. This time, instead of calling this point here some value, a horizontal distance away from x, I'm calling this x, and I'm calling this value here c. And what this does is this allows me to write my difference quotient as f of x minus f of c, all of that over x minus c. I am still finding the vertical change, and I'm still finding the horizontal change. That has not, pardon the pun, changed, right? I'm still doing rise over run, if you will. But I'm simply relabeling the way I think about my terms or my coordinates. And what this allows me to do is by not looking at the difference quotient as h goes to 0, but rather as x approaches c, the limit as x gets closer to c, what I'm able to do is I'm able to find the numerical value for the instantaneous rate of change at x is equal to c. This is not dramatically different. So to really compare the two, the formal definition of the derivative here, the formal definition of the derivative gives me a function that helps me find the derivative, the slope of the tangent line at any point. The alternate definition of the derivative jumps straight to finding the numerical value for the slope of the tangent line, or what we call the instantaneous rate of change at that point. That's the main difference. So let me highlight doing one problem using the alternate definition here. So let's use the alternate definition to find the slope of the tangent line at this point, also known as f prime of 3. So I'm going to write that. It's the slope of the tangent line at x is equal to 3. All right? So what we're going to do, we're going to find the limit as not h approaches 0, but as x approaches c. And what is our c value here? It's 3. So we're going to write f of x minus f of 3, all of this over x minus 3. So let's rewrite this. What is f of x? That's just our function, which we're told is x cubed. What is f of 3? Well, it's our function evaluated at 3, so 3 cubed. All of this over x minus 3. And again, if you try to do direct substitution right now, you'll get indeterminate form. But we can actually rewrite using the difference of cubes. We can say that this is x minus 3 times x squared plus 3x, all of this plus 9 over x minus 3. That's just the difference of cubes. We can divide these out, and we're left with, change that color, we're left with the limit as x approaches 3 of x squared plus 3x plus 9, which if you plug that in, 3 squared plus 3 times 3 plus 9, that's going to be equal to 27. So using the alternate definition of the derivative, we can find the numerical value of the instantaneous rate of change at a specific x value, which in this case, the slope of the tangent line at 3 for the function x cubed was 27, or is 27.